Welcome back for the fourth installment of the AP ECE Chemistry Chapter 13 Acids and Base Problem Set. We're going to take a look at problem 59. In problem 59, you're asked to consider a weak acid that's diprotic with a Ka1 of 2.7 times 10 to the negative fourth and a Ka2 of 8.3 times 10 to the negative seventh. You're asked to find the pH of a 0.2 molar solution of this diprotic weak acid and then estimate the concentration of the singly dissociated Ha minus and then a doubly dissociated A2 minus. So as usual, I advise writing equations, a couple of them even. H2A will be in equilibrium with H plus and also HA minus, and we have a Ka associated with that one. That's our first one, Ka1, 2.7 times 10 to the negative fourth. And then write a second equation for the HA minus dissociating into H plus and A2 minus with Ka2 of 8.3 times 10 to the negative seventh. Assume that almost all of the H plus is actually going to come from the first dissociation and make a nice table from that. So we'll use our first equation that we got in this little subpart number 1. H2A gives H plus and HA minus, and with the Ka1 of 2.7 times 10 to the negative fourth, we start to plug in values. We know the original concentration of the H2A is 0.2. Assume that we have no hydrogen ion and no conjugate base of the H2A. So we'll get a minus x plus x, and at equilibrium, in molarity, it'll be 0.2 minus x, and then for the H2A, and then x and x for both the hydrogen ion and the conjugate base of this H2A. Then you write a Ka expression and solve out for x. And so you are going to use the Ka1 and then plug in the values we know. We assume that this is an x, and this little bottom right here, this x minus x, the 0.2 for the H2A can get subtracted away. We solve out for x as 7.4 times 10 to the negative third, and that'll be essentially our H plus concentration. So then you can find the pH by doing the negative log of that. The pH should be 2.13. H plus will actually equal the concentration of HA minus, and that might not be obvious from right away, but if you look at the ICE table, then you can figure out what the HA minus would be. So if we go back for a second, H plus came out to be a certain concentration. We said 7.4 times 10 to the negative third, and well, HA was X as well, so it should be 7.4 times 10 to the negative third also. You can use the second equation that we had from before, which is the HA minus dissociating to become the H plus and A2 minus, and the second Ka that we have, to then further go on and find out what the A2 minus concentration is. Since we know what the HA concentration is, and that's what we estimated in number 6 here, HA minus, and we know what the H plus concentration is because we found it out earlier because it almost all comes from the first dissociation of it. We actually have most of the Ka expression here with H plus, A2 minus, and HA minus in, so we just solve for A2 minus as 8.3 times 10 to the negative seventh molar. Let's take a look at problem 73. In problem 73, you're considering codeine, which is being abbreviated COD, as a weak base. So I say write an equation for this. It's COD plus H2O gives you HCOD plus and OH minus. The Ka for the conjugate acid is 1.2 times 10 to the negative eighth. So you're asked what is the Kb. Ka times Kb for a given acid-base pair will equal Kw, so you can rearrange algebraically. Kb will equal Kw divided by Ka. Therefore, it's 1.0 times 10 to the negative 14th divided by the Ka 1.2 times 10 to the negative 8th, and we get a Kb of 8.33 times 10 to the negative 7th. You're then asked to find the pH of a 0.002 molar solution of the codeine. I say 1, use an ICE table, so here's the setup of the ICE table, and look, I put the Kb there as well. Then try to solve a Kb expression to solve for x. We know what our original concentration of the codeine is. Assume nothing for the HCOD and nothing for the OH minus. We'll do plus x as the change for these, and minus x as well. Then we start to funnel in these values into our Kb expression here. So we wrote the expression down here and solve for x. Again, we can assume this x on the bottom is 0 here. We solve for x, and be very, very careful here, because x is not H plus ion concentration, because we're dealing with a Kb expression. X is actually OH minus ion concentration. It's 4.08 times 10 to the negative fifth, so you can actually find the POH, and the POH is 4.39, and then you find from that that the pH is 9.61, which is what the original problem was asking for. So it's really important if you put the KBs or KAs with the expression, it kind of cues you in as to what thing you're supposed to be using for the remainder of your solving of these problems.